As it turns out that Ben's topic, learn to think about your data as a knowledge graph, is very topical because both of our talks this morning have uh, introduced the notion of connected data and graph technology. So, Ben, why don't you tell us a bit more about what it takes to work with your data in a graph form?
Yeah, absolutely. Thank you, Tony. Thank you for the opportunity to come in here and share a bit about this. I'm the CTO of GraphGrid. I've been working with connected data now for about 10 years, specifically labeled property graphs and knowledge graphs. And what we're going to cover today are kind of four key areas. First, like what is a knowledge graph, because there's a lot of different definitions that you'll hear using your data as a knowledge graph, how to get started with it and thinking about it in a quick way. And then how do knowledge graphs prepare your data for AI and machine learning? So part one here, you'll hear a lot of different varied perspectives on knowledge graphs. If you talk to somebody in data management, they're typically more concerned with the creation, use, and representation of metadata. Ontologists, they're really, and knowledge engineers, they think about the conceptualization of a domain. So what does it mean? What are the semantics associated with that domain? Business users are really interested in knowledge graphs for the hidden insights that can be surfaced by utilizing the links that are within the data and the relationships there. So just real quick, what a knowledge graph is not. It's not, pie charts, bar charts. These are actually charts, but in our language, how we're taught, these get referred to as graphs. But graphs connect data, charts plot data points. It's a simple way to keep them separate. So let's start with a unified definition of a knowledge graph. It's really a connected structure that represents real-world people, places, things, and the way in which they are all related. So that's the key context that connecting your data brings it into. So with this image here, it's kind of the traditional where graph theory originated in the Seven Bridges of Königsberg, but you see how a real-world problem there can be kind of abstracted out to be connected and represented as each landmass, the seven bridges, the connections across them. The landmasses become the nodes, so those are different places, and how they're connected are the bridges, right? And so you kind of see this evolution going from something in the real world to a abstraction to people, places, and things, and then the context in which they're connected. And anything that we interact with today is really a graph. I see graphs all over the place. From the internet to you and your relationships with your family, your friends, your favorite coffee shop, to biology, molecules, chemistry, etc. Like all of these things are graphs. And now, in order to make graphs useful to us, really we start to talk about knowledge graphs in that context, and we give ourselves a few building blocks to work with. So nodes are the actual representation. Our labels, which are kind of categorizing nodes, so a person, an organization, those would be examples of labels. Edges, that's the way things are connected, so the person could be the employer or employee at an organization, which would be like the edge type. And then properties are your metadata. So if we break that down a little bit more, to start thinking about your data as a knowledge graph, we have our nodes, so person. So nodes, again, are people, places, and things. So that's a node in the graph, the person, the hotel, the room. This allows us to connect real-world things in context. So there's a node is your actual data elements, and labels organize those nodes. So person here would be an example of a label. It's a way to organize it into subgroups so that we can ask questions or introspect our graph in a bit more intuitive way. The edges then, so a person prefers this hotel, and this hotel has available rooms. Those are meant to be, semantically meaningful in context. All edges are directed, they're typed. They always have a start and an end node. You can't just have floating edges, or you shouldn't really, because it's not super practical in a typical real-world use case. And then both nodes and edges get properties. So we have Jane Smith prefers this hotel, the Hilton, right? Room number 315 is available. So we can start to represent this real-world situation and see how it flows through the context of a knowledge graph. So now that we have the basic building blocks, we're going to start looking at how to use your data with a knowledge graph. So one of the key things is always picking the right storage engine. As graphs have become more and more popular over the years, we have a couple different approaches. So everybody, traditionally has their data in tables, and those rely on indexes to connect data elements. So if we have Jack and Jill's house, in a graph that does not rely on indexes to move between data elements, I could go directly from Jack's house to Jill's house. But if I'm in a SQL system or any system that relies on indexes to move between data elements, I would have to go to a central index to look up Jill's address first and then go to her house. So with index, it's referred to as index-free adjacency, but essentially in a graph, one of the key things for highly connected data is being able to move very quickly between or directly between those data elements. What a relational system or any system that relies on an index doing is everybody that wants to move through the town, even if you know where Jill's house is, Jack still has to go to that central index, stand in line with everybody else, get Jill's address, and then go to her house. No matter how many times he's gone to Jill's house, always has to go through that same process. So it becomes very slow and very, very challenging. So picking a storage engine for highly connected data is important. We've been using Open Native Graph Database, which is open source by a nonprofit organization called the Graph Foundation. It's came out of a fork from Neo4j before they went closed source. So open source is really important to us, and that was one of the ones that we've used. It does have that index-free adjacency. Tables do not have index-free adjacency. They use foreign keys to connect data elements, and so you're always connecting across some lookup table if you're linking, a person and an address together. So we'll talk a little bit later about how tables can convert to graph and how you can see those concepts and translate them to a graph structure. But when you have very highly connected data, it's important to not rely on indexes to do traversal. And so those indexes are too slow, and the graphs allow you to do rapid traversal around connecting people, places, and things. So as we move into what does it look like to get started with knowledge graphs here, now that we kind of have a little bit of a foundation. So in some ways, knowledge graphs and tables are similar. What you see here is a mapping where tables have rows, knowledge graphs have nodes. So the actual nodes that get stored into the graph are essentially represent a data element, which a row in a table represents a data element. Joins in tables are essentially how you link two data elements together. But in a knowledge graph, relationships link your data elements together. Tables are given a name, which we think about conceptually. If we have a person table, it probably stores persons, right? So in a knowledge graph, we use labels to organize the different data concepts or data types. So maybe we have a person label. Nodes can have more than one label. So they could be a person, but they could also be an actor or a director, something like that. And then lastly, tables have columns, and those essentially represent the properties or attributes that are on each element in the row. And knowledge graphs have properties. And that's how we think about the attributes that get associated to a specific data element. Some of the key ways that they're different, really. In a table, every row gets the same set of attributes, and so you often have rows that are null, maybe, so that you don't have a certain attribute, but they always have to. It still has to be allocated and stored so that that row has that attribute available to it. In knowledge graphs, nodes with the same label aren't actually required to have the same set of properties, which is really useful as you evolve and expand your schema, your model, because you don't have to go through a large migration to be able to give every node a new property. But then on the flip side, you do have to be able to handle that empty case where essentially if it doesn't exist, it's a null consideration. But it's very manageable, and the flexibility that you get is well worth that that variation there. So for tables, joins are calculated at query time, which is part of what adds to the challenge in performance. But if you take those joins and when we store them in a knowledge graph, they get stored as relationships, and those are persisted first-class citizens within that database structure, and so we get to take advantage of those always being there, always being present, and take advantage of that rapid traversal directly across the relationships. Lastly, a row can belong to one table, but a node can have many labels, so nodes can belong to more than one concept. If we just look at a structural comparison visually, so if we have our records in the blue, and we have the dotted lines, which are kind of the soft relationships of the joins that are put together to connect everything at query time, those records become the nodes, and then those joins become the hard relationships that actually get persisted into the graph. In a table world, we try to model, and so in how we model, we try to make things ideal at the start and try to avoid changes, because as you make changes to the table, there's a ton of migration that has to take place. There's certain scenarios where if you have billions of entries in a table and you try to add another column, maybe it won't finish in our lifetime. You run into scenarios like that depending on the size or the amount of your data that you have. In a knowledge graph, the schema can evolve with your application, and as you have things change. So it's really flexible, and it lets you adapt at the pace of business or pace of the mission. One of the other things with Graph that's really beneficial is it breaks down the barriers between business and technical. And so when we model, it's very whiteboard friendly, and we can talk directly about example use cases that we have and how those are related. So we talk about real world people, places, and things instead of dealing in the abstract when we're first putting the model together. And then usually we'll take a step to extract it out to more of a meta model. So if we just do a quick model comparison, if we have data in tables with players that have columns for ID, name, and position, we have down here on the bottom a player node where they have name and position, and then instead of this join here to transfers, we have a direct transfer node, which is something that would get an ID. It's a direct entity, and then we have this of player and from club to club, so it's linking them directly. But because these relationships are persisted and we can traverse from one node to the next without using indexes, it becomes a very intuitive representation visually, and if we're modeling and talking about it, but also from a performance perspective and how we query about it and how we store our data. And it becomes something that each one of these nodes, the club node, the player node, they can connect to many other things. Maybe the player has a social media account, and they had all of that portion of their social communication, or the club has other players that are playing for it currently, or other transfer agreements. So you can kind of see how it just spans out and provides a really powerful representation of the data. So as we start to think a little bit more about how we go from kind of this table-centric world where a lot of our data looks like Excel, even if it's in a database, it still looks like Excel in the way that it's stored. We're going from kind of some SQL language where you're selecting from some table where this player's name is, and you're going to join it to something else. But in Graph, you're more focused on the data that you have. So when you start transitioning to Graph, you're getting out of the mindset of joins and tables and select star or select these properties to, okay, I want to match, so I want to look up some player that has, or some node based on the label type, based on some property, and then that's where my starting point is. That gets me my starting point in the graph, and then I'm going to, return that node. So it's a very intuitive language for technical and non-technical. If we take our example from the previous slide and expand out just a little bit, we're going from selecting these players from the transfer, and now we have to join because we want we have to match up our IDs. So this is where that journey to the central index takes place, where we're going from from club to this club, connect these IDs, connect these IDs, connect these IDs. In graph, down at the bottom, when we start thinking about our data in a connected state, you can see that the parentheses kind of look like nodes. This square braces are kind of like your relationships. It gives you a much more intuitive connection to the data that you're actually querying and asking questions about. So we're going to match, some club that's the from club across this relationship where this transfer took place from this club to this club, and the transfer was of this player. And so it really provides a much more intuitive way to work through your data and work with it for your developers, for your analysts, anybody, any one of those individuals can definitely learn the graph query language and work with it in that structure, and you don't have to go through the join pain of working across those. So what we have here is kind of the country ID, countries, confederations, country ID. And if we took our model from before where we had this transfer that was of this player from this club to this club, now we can say, oh, this player plays for this country, which is part of this confederation, and this club is part of this country, and so is this club. And we can very easily expand out our graph model here to represent this additional data. So if you have, and then similarly, we can update the queries. So we have some additional joins, but then we can look at each club or the player plays for the country, part of that country, so on. So when we're translating a table-centric schema, there's a few questions to consider. So in this case, we're using the Northwind data set. We're looking at suppliers, products, employees, territories, regions, orders, order details, categories, customers, shippers, etc. And when we're starting to work with our data as a knowledge graph, we should think about, are the tables and the table names representative of the actual entities that we want to have in our graph? Are there any that we want to get rid of? Do we need any new entities? Do we need all the tables, all the fields? And when we go from a kind of entity relationship diagram like this is, the easiest way to think about it is to start with the foreign keys. So any place we have references or IDs across it, we're going to get rid of the foreign keys. So drop all of those because we're not going to have those existing in our graph schema. And we want to locate join tables. So the join tables, essentially, we know those will become our relationships because we talked about the joins being kind of a soft structure in our data, when really there's an explicit relationship that should exist. So we look at those join tables, and from this one, on the right, we're going from employees represents a specific territory. So if I just toggle back, we can see that we have this employee territory join table, and we're going to, instead of the foreign key IDs in both of those, we're just going to say, okay, well, some employee represents a territory. That's simple enough. And then up here on the left one, we had this other join table, order details, where we had additional properties on it. And so those will just become a relationship with properties. So we'll have an includes, so order includes products, and we're putting the properties there on that relationship. So if we work through kind of the entire example of the graph here, so if we go from categories and products, order details, suppliers, customers, employees, orders, shippers, territories, and we translate that to a graph model, this is one example of what it might look like, where we have some product that is in a category, we have a supplier that supplies this product, and we have a shipper that shipped an order, which includes a product, an employee sold this order. Then we have an employee reporting hierarchy where some employee reports to another employee, and so on. And this employee represents the territory, which is in a region. And so we've taken, our tables on the left and broke them down into very specific relationship types with direct connections that can be traversed without using indexes. And it does, you heard the way I talked through it, it sounded very much like plain English, and that's largely because it is. When you have the graph model represented, it does allow us a very rich representation of real world people, places, and things, and it does break down communication barriers across all levels of the business, which is one of the really useful things that we've found, and it provides a lot of clarity and ease of building fairly complex, really complex systems, to be honest. Just about being able to solve problems that are dealing with highly connected data where traditional data representations and structures wouldn't work out so well, or would be challenging to work with. So lastly here, knowledge graphs prepare your data for AI and ML. So the main thing that graphs give you in this regard is structure, distance, and context. Structure deals with what the graph, a node, and the properties around and relationships around it. So person, how they're, and everything that they're connected to. And then you have local and global structures within the graph. Distance deals with how far away things are. So if you have cause and effect chains, or you're just looking at, what are different pathways, friend of a friend of a friend, different structures that are distance, you can use those as part of understanding, part of the vector that goes to a machine learning or AI model. So, non-indexed based graphs don't support really distance in this way in their representation. And so this really allows you to get to incorporate distance that you wouldn't otherwise see in your data. So the graph does enhance your data in this way, which can then be used as a vector, as a graph embedding that goes to a two-dimensional output for an AI or machine learning model. And lastly, context. And this is really the situation or meaning behind it. And one of the things that graphs let you see is, not only inferred relationships. So if Jane, files a tax return that has a 1040 that references a K1 that references this LLC, well, we can say, oh, Jane owns this LLC. And if Jess files a W-2 that was sent by this LLC, we can say that this LLC employs Jess, right? And then similarly, it also tells us what we don't see, right? So if we have this 2018 tax return, but it doesn't report a W-2, and the LLC reports a W-2, we can also identify that there was something missing, because we do expect an explicit relationship in that regard. So these are all contexts that can then be sent out to graph embeddings for AI and machine learning models. Journey mapping is another one that graph structures are useful for when you think about different events where, if a job loss occurs, maybe no payment is made, maybe they get a notice, maybe they call a support center, make another call, maybe an installment agreement, and so on. So you go down through, and it can kind of map journeys, and then that can be used to further enrich understanding and training data for different AI models. And ultimately, one of the enhancers and enrichment items that we get with graph is being able to introduce trait fields. So a lot of complex relationships or substructures within the graph can be simplified down to different traits that can then sit between two node types, which is your basic structure for recommender systems that can be used, and these trait fields can be used to tie out and be sent out to machine learning models as well when we start looking at similarity analysis or those types of things. It's a simplified representation of it for these entity comparisons. Just a quick overview of graph embedding for AI models. So essentially what we're doing is we have some graph domain where we have all these connected people, places, and things, and we simplify that down to a vector structure to get it into a two-dimensional space. So the reason that we do this is because there's a lot of existing AI and ML models out there that can benefit from enriching the data in a graph first, so you get that structure, distance, and context before you actually feed the data into the AI model. It's one of the maybe not so intuitive things, but by translating your data into graph and doing that enrichment, you actually get better use with your, you get better performance by your AI and ML models by thinking about your data as a graph and taking the time to model and represent it. One of the things that it can be used for is that similarity analysis and journey mapping. So if you have a new individual patient that comes in and you do the similarity analysis across similar patients, you can start to look at their outcome, their journey comparison, event progressions, and then identify, well, what's the projected journey? What's the most preferred journey or the probable event for this patient? And then what's the best next step to lead them on as they go through that. So that was kind of a brief overview, real quick, and just under 30 minutes. I got a few minutes left for Q&A. I kind of flew through that, so happy to take any questions that anyone has.